Section 5.1, The Nature of Energy. Although the idea of energy is a familiar one, it's a bit challenging to deal with the concept in a precise way. Energy is commonly defined as the capacity to do work or to transfer heat. This definition requires us to understand the concepts of work and heat. We can think of work as the energy used to cause an object with mass to move against a force, and heat as the energy used to cause the temperature of an object to increase. We'll consider each of these concepts more closely to give them fuller meaning. Let's begin by examining the ways in which the matter can possess energy and how that energy can be transferred from one piece of matter to another. Topic 1. Kinetic energy and potential energy. Objects, whether they are tennis balls or molecules, can possess kinetic energy. The energy of motion. The magnitude of the kinetic energy, E sub k, is an object depends on its mass, m, and speed, v. E sub k equals 1/2 mv squared. Equation 5.1 shows that the kinetic energy increases as the speed of an object increases. For example, a car moving at 55 miles per hour has a greater kinetic energy than it does at 40 miles per hour. For a given speed, the kinetic energy increases with increasing mass. Thus, a large sport utility vehicle traveling at 55 miles per hour has greater kinetic energy than a small sedan traveling at the same speed, because the SUV has greater mass than the sedan. Atoms and molecules have mass and are in motion. They therefore possess kinetic energy. All other kinds of energy, the energy stored in chemical bonds, the energy of attraction of north and south poles of magnets, for example, are potential energy. An object can possess potential energy by virtue of its position relative to other objects. Potential energy arises when the force operates on an object. A force is any kind of push or pull exerted on an object. The most familiar force is the pull of gravity. Think of a cyclist poised at the top of a hill as illustrated in Figure 5.2. Gravity acts upon her and her bicycle, exerting a force directed towards the center of the earth. As the top of the hill, the cyclist and her bicycle possess a certain potential energy by virtue of their elevation. The potential energy, E sub p, is given by the equation E sub p equals mgh, where the m is the mass of the object in question, in this case the cyclist and her bicycle, and h is the height of the object relative to some reference height, and g is the gravitational constant, 9.8 meters per second squared. Once in motion without any further effort on her part, the cyclist gains speed as the bicycle rolls down the hill. Her potential energy decreases as she moves downward, but the energy does not simply disappear, it's converted to other forms of energy, principally kinetic energy, the energy of motion. This example illustrates that forms of energy are interconvertible. Gravity is an important force for large objects such as the cyclist and the Earth. Chemistry, however, deals mostly with extremely small objects, atoms and molecules. Gravitational forces play a negligible role in the ways these submicroscopic objects interact with one another. Forces that arise from electrical charges are more important when dealing with atoms and molecules. One of the most important forms of potential energy in chemistry is electrostatic potential energy, which arises from the interactions between charged particles. The electrostatic potential energy, E sub EL, is proportional to the electrical charges on the two interacting objects, Q1 and Q2, and is inversely proportional to the distance separating them. Here, K is simply a constant of proportionality, 8.99 times 10 to the 9th joule meters over Coulomb squared. Coulomb, C is Coulomb, the unit of electrical charge, and J is the joule, a unit of energy that we'll soon discuss. When dealing with the molecular level objects, the electrical charges Q1 and Q2 are typically on the order of magnitude of the charge of the electron, 1.6 times 10 to the negative 19 coulombs. When Q1 and Q2 have the same sign, for example, both are positive, the two charges repel one another, pushing them apart. El is positive. When they have opposite signs, they attract each other, pulling them towards each other. El is negative. The lower the energy of a system, the more stable it is. Thus, the more strongly opposite charges interact, the more stable is the system. One of our goals in chemistry is to relate the energy changes that we see in our macroscopic world to the kinetic and potential energy of the substances at the atomic or molecular level. Many substances, fuels for example, release energy when they react. A chemical energy of these substances is due to the potential energy stored in the arrangements of their atoms. Likewise, we'll see that the energy of a substance possesses because of its temperature. Its thermal energy is associated with the kinetic energy of the molecules in that substance. Section 2. Units of energy. The SI unit for energy is the joule, in honor of James Joule, a British scientist who investigated work and heat. 1 joule equals 1 kilogram times a meter squared per second squared. A mass of 2 kilograms moving at a speed of 1 meter per second possesses a kinetic energy of 1 joule. E sub k equals 1/2 mv squared equals 1/2 2 kilograms times 1 meter per second squared equals 1 kilogram meter squared over second squared equals 1 joule. A joule is not large enough amount of energy, and we'll often use kilojoules in discussing the energies associated with chemical reactions. Traditionally, energy changes accompanying chemical reactions have been expressed in calories, a non-SI unit still widely used in chemistry, biology, and biochemistry. A calorie was originally defined as the amount of energy required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. A calorie is now defined in terms of the joule. 1 calorie is exactly 4.184 joules. A related energy is used in nutrition is the nutritional calorie. Note that this unit is capitalized. 1 calorie is equal to 1,000 calories, or 1 kilocalorie. Topic 3. System and surroundings. When we analyze energy changes, we need to focus our attention on a limited and well-defined part of the universe to keep track of the energy changes that occur. The portion of that we single out for study is called the system. Everything else is called the surroundings. When we study the energy change that accompanies a chemical reaction in the laboratory, the reactants and the products constitute the system. The container and everything beyond it are considered the surroundings. Systems may be open, closed, or isolated. An open system is one in which matter and energy can be exchanged with the surroundings. A boiling pot of water on the stove without a lid is in an open system. Heat comes into the system from the stove, and the water is released to the surroundings as steam. The systems we most readily study in thermochemistry are called closed systems. A closed system can exchange energy but not matter with the surroundings. For example, consider a mixture of hydrogen gas, H2, and oxygen gas, O2, in a cylinder, as illustrated in Figure 5.3. The system in this case is just the hydrogen and the oxygen. The cylinder, piston, and everything beyond it, including us, are the surroundings. If the hydrogen and oxygen react to form water, energy is liberated. 2H2 gas plus O2 gas yields 2H2O gas plus energy. Although the chemical form of the hydrogen and oxygen atoms in the system is changed by this reaction, the system has not lost or gained mass. It undergoes no exchange of matter with the surroundings. However, it can exchange energy with its surroundings in the form of work and heat. An isolated system is one in which neither energy nor matter can be exchanged with the surroundings. An insulated thermos containing hot coffee approximates an isolated system. We know, however, that the coffee eventually cools, so it's not perfectly isolated. Section 4. Transferring energy, work and heat. Figure 5.1 illustrates the two ways in that we experience energy changes in our everyday lives, in the form of work or heat. In Figure 5.1a, energy is transferred from the tennis racket to the ball. changing the direction and speed of the ball's movement. In Figure 5.1b, energy is transferred in the form of heat. Indeed, energy is transferred between systems and surroundings in two general ways, as work or heat. Energy used to cause an object to move against a force is called work. Thus, we can define work, W, as the energy transferred when a force moves an object. The magnitude of this work equals the product of the force, F, and the distance, D, that the object has moved. Equation 5.3, work equals force times distance. We perform work, for example, when we lift an object against the force of gravity or when we bring two like charges closer together. If we define the object as the system, then we, as part of the surroundings, are performing work on that system, transferring energy to it. The other ways in which energy is transferred is as heat. Heat is the energy transferred from a hotter object to a colder one. Or, stating that the idea is in a slightly more abstract but nevertheless useful way, heat is the energy transferred between a system and its surroundings because of the differences in temperature. A combustion reaction, such as the burning of natural gas, illustrated in Figure 5.1b, releases the chemical energy stored in the molecules of the fuel. If we define the substances involved in the reaction as the system and everything else as the surroundings, we find that the released energy causes the temperature of the system to increase. Energy in the form of heat is then transferred from the hotter system to the colder surroundings.